Hi everyone. Today we'll be building object detection system using Python and OpenCV. As a context, object detection can be explained as a tool that brings a magic of how computers see and understand images and videos. You can imagine your smartphone recognizing and tagging faces in your photos, or self-driving cars like Tesla detecting pedestrians on the road. Those are some of main applications of object detection. We will be using Google Colab for this project, which is a hosted Jupyter Notebook service that requires no setup to use and provides free access to computing resources. If you do not have a Colab account, you can create a free account by signing in with your Google account at colab.research.google.com. I'll put this link in the description box below. I will show you everything step by step. I'm sure this will be fun and helpful project to you. If you stick around until the end of this video, you will be able to build your own object detection system with Python and OpenCV so that you can add it to your resume or portfolio and even show it to your potential employers. Before getting started, I would like to say that I would really appreciate if you could subscribe, like, and click on the notifications bell to see more videos like this in the future. So let's get started. First off, let's start a new notebook by going to the Google Colab. I have some other projects here. Your interface might be a little bit different from mine. So let me create a new notebook by pressing this button here. And after loading, let's rename it here as object underscore detection. Object underscore detection. And from here, to get started, we need to install OpenCV, a popular computer vision library that provides tools for image and video processing. As you can see here, we can do that by saying import CV2. And then to display our images directly in the Google Colab, we have to import CV2 underscore IamShow, as you can see here, because we cannot use cv2.imshow function as in the desktop environment. Then, after importing OpenCV and cv2 underscore IamShow, let's upload a picture, in our case a cute cat picture, to our directory. And now we can read that image file using this. Here, cv2.imread. It's a function. It's part of OpenCV library, which helps us to read an image from a file. And cat.jpg is a file path or a file name of the image we want to read. In this case, it's an image file we just upload to our directory here, if you check it. And also here we are assigning the result of this function to img. So let's run this. We just imported cv2 underscore IamShow earlier. Now we can use that to display our image in this Google Colab environment, in this notebook. And after displaying the image here, cv2.waitKey0 is used to wait for a keyboard event. The argument 0 indicates that the program will wait indefinitely until a key is pressed. This is a way to keep the image window open until you press a key, preventing it from closing immediately. In a typical desktop environment, we cannot use, we'll be using cv2.imshow instead of this function here, cv2 underscore imshow. And cv2.waitKey is used to manage the display window. However, in the Google Colab, the standard cv2.imshow function doesn't work, so here we are using this function to display in our Google Colab environment. So let's run this and see our picture if we have read it correctly. Oh, cool. Here we can see our cute cat. Now we'll be seeing our detection model can detect this cat. Before moving on to the next part, let me explain 3 more files I have uploaded to our directory in order to make our system work properly. First one is coco.names here. Maybe you are familiar with this. This file typically contains a list of class names. The Coco dataset is a widely used dataset for object detection, and coco.names would contain the names of the classes in that dataset, Coco dataset, such as person or car or cat here in our case. And our second file here This ends with which ends with PB. This file usually represents the frozen graph of a trained neural network model. A frozen graph is a TensorFlow model that has been converted into a format that's optimized for inference. If it's a little bit complicated to understand, don't worry. You can still run your code without understanding all of this now. And our final file here, it actually has a pbtxt extension, even though it's not really visible here. It usually provides details about the model's configuration, such as input size, anchor boxes, and other parameters. You can find all of these files in open source communities like GitHub, or I myself will even upload this to my GitHub. So if you want to download and play around, you can find them from there and play around. Back to coding, let's first initialize a list named class names that will be used to store the class names read from the file. And here we are specifying the file name coco.names from which the class names will be read. Now let's open the specified file coco names in a read text node RD using a context manager with statements. The use of a context manager ensures that the file is properly closed after reading, even if an error occurs. And the last line here reads the content of a file using f.read function, removes any trailing newline character using the \n using rstrip \n, and then splits the content into a list using split \n. The result is a list of class names where each class name corresponds to a line in the file. Now let's see if we have read class names from our coconames file properly. We can do that by printing list of class names that we initialized earlier. Let's run this and see how it goes. Nice. We can see here different class names from the Coco dataset. We have traffic light, fire, and even NA. And we have cat, dog, and different animals. Nice. Now let's define file paths for configuration and weights files associated with object detection model. Specifically, single-shot multi-box detector (SSD) model based on MobileNet v3 architecture and trained on the Coco dataset. And here also, like, we are setting the variables config paths and weights paths, as you can see. And also, as I just explained earlier, these two files, pbtxt file and pb file. pbtxt file, it provides details about the model, and the frozen graph file, which is like pb file, contains an actual model parameters. These files are a part of a pre-trained model package, and we can use them to load the trained model for object detection tasks without retaining from scratch. It makes our work easier, even though it has its own trade-offs. Now it's time to configure the deep neural network model for object detection by setting the input size, scale, mean values, and channel swapping according to the requirements of our pre-trained model being used. These settings ensure that input images are pre-processed correctly before being fed into the neural network for object detection. First, let's create an instance of the CV2 DNN detection model class. It's part of OpenCV's deep neural network CV2.dnn and is assigned specifically for object detection tasks. The weights path and config path parameters are file paths to the pre-trained weights and configuration files for the model, respectively. This line essentially loads the pre-trained model for object detection. Next, let's set the input size for neural network to 320. The input size represents the dimensions, width, and height of the image that will be fed into the neural network for detection. In this case, the model expects input image to be of size 320 pixels. And also then let's input scale, mean values for neural network, and last line here specifies whether to swap the red and blue channels in the input image. OpenCV actually typically use the BGR color order, but some pre-trained models might expect RGB. Setting this to true swaps the red and blue channels. After setting all of this, let's run this. All right. Now let's go ahead and try using the detect method from OpenCV. This method here is used to perform object detection on the input image IMG here using the pre-trained neural network net, and the conf threshold here it's set to 0.7, which means that only detections with a confidence percentage higher than 70% will be considered. And we have class IDs here. This variable will contain the class IDs of the detected objects. Each class ID corresponds to a specific type of an object that the model recognizes. For example, class ID 1 might represent a person, and class ID 2 might represent a car, and so on and so on. And we have confs here. This variable will contain the confidence scores associated with detected objects. A confidence score indicates how certain the model is about the correctness of detection. A higher score typically means a more confident detection. And BB box, this variable will contain a bounding box of the detected objects. Each bounding box is represented as a set of 4 values: x, y, width, and height, specifying the position and size of the bounding box around the detected object in the image. After executing this line of code, class IDs const and BB box, bounding box, will contain the information about the detect object in the input image, allowing us to further process or visualize results, such as drawing bounding box around the detect objects, as you have seen earlier, like when I was showing, based on the information that we'll be having. Now let's see a result of object detection by printing class ID and bounding box. We can do that by printing class IDs and box. And we can see here that class ID is 17. And if we open the class names from coco.names file from earlier, like we can see that class ID 17 is cat. But let's try drawing a rectangle bounding box around the cat we detected. To do that, let's create a loop that iterates over the detect objects, draws a bounding box around them, and adds a label with the class name and the confidence score to the image. Here, and this line unpacks the values x, y, width, and height for the w and h from the box array, which represents the bounding box coordinates for the detect object. And here, this line draws a rectangle around the detect object on the image. The coordinates are specified by xy for a top left corner and x plus w, y plus h for the bottom right corner. The color parameter is set to green and the thickness is set to 3 pixels. And lastly, this line adds a text to the image to label the detect object. It includes the class name, which is retrieved from the class names list, and positions x plus 10, y plus 30 for the text. Let's see how it goes, and font scale of 2, green color, and thickness of 2 pixels. This loop should effectively process each detect object, should draw a bounding box, but let's see how it goes. First, let's run this. As we just did in the beginning of this tutorial, let's display our image using cv2 underscore imshow function. And let's run this. And voila, we can see our cute cat detected. I'll put this source code in my GitHub and you can try detecting other things by uploading other pictures on your own. If you are here until this part of tutorial and it has helped you, I'm really happy for that. Now you can build your own object detection system with Python and OpenCV. Before we want to close this, I have some upcoming projects and would love to hear your voice on what should I work on next and create a tutorial like this one. Feel free to comment below one of these ideas or your own. And also it would be so helpful if you could subscribe, like, and click on the notifications bell to stay informed with my upcoming projects and tutorials like this. Also, if you'd like to see more of a computer vision project, I suggest checking out my other video on face recognition with Python. As always, thank you and see you next time.